Good afternoon, ladies and gentlemen. I am going to present a paper about a component, not material. In particular, the paper deals with the additional loading condition due to dynamic effects in gears. The object of the paper is a transmission for electric vehicle. In particular is differential, and we have simulated the behavior of the train gears, ordinary train gears, in input to the epicycloid. Why dynamic effect in electric vehicles? Because electric engines have an high velocity, and so the input velocity in the transmission is so high to have the problems related to the overload for dynamic effect. Overload is an high force in the gear meshing. Aim of this paper, two aims of the paper: to calculate a number that can interpret this overload condition. So, as an example, the KV dynamic effect of standard. But we have calculated this number, this overload, by means of classical formula, but also by a multi-body simulation. A multi-body simulation that may obtain the gear meshing during a period of time. In this work, we have used two different kinds of multi-body simulation. We have simulated the gear as completely rigid. So, gear and teeth completely as a system without any flexibility. And then we have taken into account of the flexibility of only the teeth. So here you can see the transmission. You see the design, and in particular gears 1, 2, the first engagement, and 3 and 4, the second engagement. In this paper I present the simulation of the second step of velocity, so gear 3 and gear 4, in that you can you can see that this is the pinion, gear 3, this is the gear 4. Here, here you can see the differential, the sun, and etc. Multi-body here, I'm on the table, yes. You can see the multi-body motor. The vehicle has a weight less than 600 kilo, and the max speed is 90 kilometers per hour. This is an urban car. This one? Okay, thank you. Yes, it's better. Thank you. Okay, how to take into account the dynamic effect? As I have already said, ISO standard suggests three methods. The method A, that means you can utilize what you want. As an example, experimental activity, or as in this case, a numerical activity. Or method B and C are traditional mathematical models. The best is method B and then method C. I think as an example for a transmission, classical industrial transmissions, it's good also method C. But if you have to take into account more dynamic effect, it's better to have a refinement of the activity. I don't present the formula. This is method B of standard. AGMA standard is quite the same. The formula, the method, is a traditional method and takes into account rotating masses, resonance range, and all parameters of the engagement, as flexibility, as damping, as also the geometry of the gear. A particular parameter that is hidden inside the formula is the single stiffness of engaged gear. This stiffness takes into account also the geometry of the wheel, of the gear. So the teeth, but also the geometry of the rim, and also the geometry of the web. And as you will see in the next paper presented by my colleague, also this stiffness may influence the crack path in a gear during its fracture. This is method C, similar. This is the tables representing the geometrical characteristic of the four gear. Modulus, pressure angle, etc. Now, simulation by multibody. This simulation is more simple. The engagement is without any parameters of contact, because the situation is contact rigid-rigid. If we can have a reasoning like a gear represented by a classical beam, we can say that the first simulation means only the effect, the local effect of the Hertzian contact. But the global movement during the engagement is quite rigid. The other simulation takes into account of the flexibility of the teeth. If we have an idea of the tooth like a beam, we can consider the local Hertzian contact, the bending, the shear, and also the effect of the stiffness of the clamping zone, that is the rim of the gear. Now the result. Firstly, the result of the analytical formula, then the result of the simulation. I have forget to say that the velocity during the trend of velocity in quite 6 seconds, we have simulated from 0 to the maximum speed of the vehicle. Here there is a calculation, the result calculated by means of a method be as a function of the velocity of the speed of the motor. Here, a constant value of method C. Here, the first simulation, rigid. We have tuned the model during the first and the second simulation by matching the forces value. The average forces values calculated by means of the classical formulas of equilibrium, and by calculating the average value during the simulation. You can see all the resonance condition, and there is evident the dynamic effect in the simulation. This is the KV factor obtained in the case of the simulation by the total force with medium value and the movement of the force respect to the medium value, the static force. The same things with the flexible rigid model. You see that the KV becomes more soft without the effect so high of the resonance in rigid condition. This is the KV value. Some conclusions. I have already talked about some aspects. In this kind of simulation, the difficulties is to tune the contact parameter of the software. But if you have a goal, as an example, to match forces or to match KV, that is not so difficult. The problem is the high computational time. You see that if you consider the first simulation, you have a number of hours, 47. If you have a flexible, rigid simulation, you have a very high computational time. As an example, in aerospace application, when it is necessary to take into account also, as an example, the modal deformation of the web, that is the modal deformation of the plate, and in some cases the plate is clamped to the shaft, and shaft and plate moves together. The computational time in flexible simulation becomes quite impossible to realize. The last aspect is that hidden inside this phenomenon and inside this KV factor, there is some information about the flexibility of the gear related to the shape of the gear. And of this aspect, my colleague will talk about. Thank you for your attention.